Let's continue to discuss how to calculate the electric field created by a continuous charge distribution. Any idea? We know how to evaluate the electric field due to a point charge and a group of individual charges as discussed in last lecture. Then how to relate the continuous charge distribution to point charges? Do you remember what we discussed earlier? When talking about an object of continuous mass distribution, we divide the object into an infinite number of elements, each which has a differential mass dm. Each mass element could be modeled as a particle. Similarly, we can divide the charged object onto an infinite number of elements. Each element contains a charge dq. This charge element is treated as a point charge. We can calculate the electric field due to one of these elements at point P, and then get the total electric field due to the charge distribution by summing the contributions of all the charge elements using the superposition principle. The electric field at P due to dq is expressed by this equation, where r is a distance from the charge element to point P, and r hat is a unit vector directed from the element toward P. The total field at P could be obtained by integrating this expression. But please note, this integration is a vector operation, and you must be very careful about the direction of the contribution from each charge element. Similar to the mass distribution of an object, there are three types of concepts for explaining the charge density based on the different charge distributions. We use the symbols rho, sigma, and lambda to represent the volume charge density, surface charge density, and linear charge density respectively. The amount of the charge element is given by these three expressions. Now let me give you some examples to show how to calculate the electric field due to continuous charge distribution. In the first example, we wish to find the electric field due to a uniformly charged rod. The length of the rod is L, the linear charge density is lambda, and the total charge carried by the rod is capital Q. Please calculate the electric field at a point P that is located along the x-axis and a distance a from one end. The rod is divided into an infinite number of charge elements. Each has the length dx. The field dE at P due to each segment of charge is in the negative x direction because every segment carries a positive charge and produces an electric field at the same direction. Hence, the sum of their contributions can be handled without the need to add vectors. As we mentioned earlier, each segment has a length dx, and the charge on the segment dq equals lambda dx. Noting that ke and lambda are constants and can be moved from the integral sign. We evaluate the integral to obtain the electric field. If P is very far away from the rod, in other words, A is much larger than L, then L in the denominator can be neglected and E reduces to this one, which is exactly the form for the field due to a point charge. It's reasonable. If point P is so far away from the rod, the shape of the rod could be neglected, so we could treat it as a point charge. Let's look at another example. The ring has a radius r and a uniform linear charge density lambda. Please find the electric field at a point P located at a distance x from its center along the central axis perpendicular to the plane of the ring. This figure shows the electric field contribution dE at P due to a single segment of charge at the top of the ring. This field vector can be resolved into two components, dEx and dE vertical. DEx is parallel to the x-axis, and DE vertical is perpendicular to the x-axis. We focus on the electric field contributions from two segments on the opposite sides of the ring. Because of the symmetry of the situation, the perpendicular components of the field cancel. We eliminate the y components of the contributions from each pair of segments. Hence, the total field can be obtained by adding all the parallel components simply. Now, let's check some special cases based on this result. At the center of the ring, where x equals 0, the field is 0. When x is much larger than r, where the point is very far away from the ring, we cannot see the ring shape of the charge. In this case, the ring acts like a point charge. Therefore, the expression reduces to this one, which is exactly the form as the one of the field produced by a point charge. Okay, let me give you one more example. A disk of a radius r has a uniform surface charge density sigma. Please calculate the electric field at a point P that lies along the central perpendicular axis and the distance x from the center of the disk. The key is to find the charge element dq in this case. We have got the formula for calculating the electric field created by a uniformly charged ring. Hence, we can describe the disk as a set of concentric rings, each of which has a surface area of 2 pi r dr. We calculate the field due to a single ring and some contributions of all rings. Because of the symmetry of the situation, the field at a point P located on the x-axis must be along the x direction. Use this result given for Ex in above example, where capital R is replaced by little r and capital Q is replaced by dq. The field due to dq is this one. Integrate this expression over the limits from 0 to r to obtain the total field at a point P. When the point is very far away from the disk, in which x is much larger than r, the disk can be treated as a point charge, and the expression reduces to the same form of the electric field created by a point charge Q. If x is much smaller than r, in this case, the expression reduces to this one, give us the near field approximation. Then, if the disk becomes infinitely large, how about the field? If r approaches infinity, the magnitude of the electric field becomes this one. This is the same expression that we obtained for x much smaller than r. We understand if r approaches infinity, everywhere is near field, so the result is independent of the position. Therefore, the electric field due to an infinite plane of the charge is uniform throughout space. Above examples showed us how to evaluate the electric field due to continuous distributed charges. The key is to find the charge element dq appropriately according to the types of the charge distribution. The total field can be obtained by summing contributions of all charge elements. Okay, see you next lecture.